We have David Mross talking about spin charge fractionalization in 2 dimensions from duality. Thank you, David. Is your mic on?
Now it's okay? Okay, well, thank you very much for putting together this very nice workshop and conference, and for inviting me to talk about my work here today. So I'll tell you about spin charge fractionalization. That's a kind of one keyword, and in relation to duality. So I'll first introduce you to this notion, spin charge fractionalization, which is a physical phenomenon which we believe occurs in various condensed matter systems. And then secondly, to the form of duality, which I will need, and then I'll put them together and see how we can use the one to describe the other. So I'm thinking about systems where I have particles which have half integer spin, like spin 1/2 and charge 1. So you can think about electrons, but also about bosons with some internal degree of freedom. And in fact, I'll be talking quite a lot about bosons and then later on turning to fermions. This is my basic ingredient. And of course, if I have such an object, if I have an object with charge 1 and spin 1/2, I can take 2 of them and form a singlet. So I get charge 2 and spin 0. Or alternatively, I can take a particle and a hole and form a triplet, and I'm getting charge 0 and spin 1. So that's not what I would call spin charge fractionalization. That's just forming composites. That's not something I'm interested in. What I'm interested in is the case where actually this object here, which carries both charge and spin 1/2, can split up into an object that carries an odd number of charge but 0 spin, or an half-odd integer spin but 0 charge. So if I have a system where I'm getting these kind of degrees of freedom, that's what I would call spin charge fractionalization. That's what I care about. So there's good reasons to believe that this kind of thing actually occurs in condensed matter systems, but I'll start with a cartoon of how can we think about an object which carries these quantum numbers actually splitting up into stuff like that. And the simplest cartoon is just in 1D. So I imagine I have some lattice, I have my particle sitting here. I have one particle per side in this case, and now I'm just forming singlets between neighbors, right? So this state is pretty simple. It has 1 charge per side, and it has spin 0 because all the spins are organized into singlets. And now I can form an excitation on the state, essentially domain wall, just like so. I'm just shifting all these singlets away, and I very simply get an excitation which carries unit charge, but there's still no spin. That's kind of a simple cartoon of how one can get something that has charge, but not charge, integer charge, but not spin, at least in 1 dimension. It's easy enough. And once I have this kind of thing, I can just put an electron in here, and I get an object which doesn't carry any charge, but which carries spin 1/2. Right? So in 1D, it's a fairly generic thing that I get these excitations which carry these fractional quantum numbers. But of course, in 2 dimensions, this is I can't do it so easily anymore. And for the rest of the talk, I'll always be thinking about what happens in 2 dimensions. So in 2 dimensions, I can still think about how I could possibly get something that exhibits this phenomenon from the point of view of some wave function, maybe. So this is some wave function, my many-body state. It has coordinates for all the up particles and the down particles. And if I have fermions or bosons, then it will be antisymmetric or symmetric under interchanging these coordinates. But there will be no specific property about interchanging up spins or down spins because they are distinguishable, right? That's some wave function. But I can take this wave function and multiply it by some other function which is fully symmetric under interchanging all possible indices. Right? Doing so will not change the symmetry properties of this wave function under interchanging up spins only or down spins only. So this thing is still a perfectly valid many-body wave function for my system of these particles. But now I have essentially one wave function which knows about the spin and one which doesn't. Right? So this may allow me to modify the state in such a way that I'm changing its charge properties by changing this guy over here without changing the spin properties at all. This would be one trial state where I can think about spin and charge separating as I'm changing this guy in some manner while keeping the other guy unchanged. And creating kind of possible ansätze for these states, that's one of the outcomes of what's called part-on mean field construction. Essentially, this is a way of generating, trial wave functions for psi s, psi c, in the hope of describing some physical system. And then one can, of course, take these trial wave functions and try them out on some Hamiltonian and see if they have the this type of wave function indeed as its ground state. That's one thing I can do, which is not what I want to do. I was going to say this is a way of, again, thinking about how this phenomena can happen. I just want to mention that one ingredient which is certainly needed to get this phenomenon is strong interactions, strong fluctuations. Otherwise, why would the electrons split up into this? And it's, the strongest evidence is probably in the vicinity of some Mott transition. Some transition where we have a transition between some insulator and some itinerant state where charge is frozen on the one side of the transition and then it becomes fluctuating. And the idea is that possibly the spin physics doesn't change so much, but the charge physics changes dramatically. So then these two degrees of freedoms may decouple and liberate. There's basically two types of such transitions which may occur in condensed matter systems. Firstly, you can drive a Mott transition by changing the particle number or changing the chemical potential, the type of transition which happen in the cuprate materials, where you can dope the system away from some Mott insulator, and then you get all kind of interesting physics directly after the transition, including the famous high temperature superconductivity. And an alternative thing, you can also drive a Mott transition by at fixed density by some other external parameter, for example, pressure. And again, you may expect that you have some transition out of a metal or a superconductor into an insulating state. And in certain cases, insulating states have some interesting characteristics which are interpreted as so-called quantum spin liquids. But from my perspective, I'm just saying I want to be somewhere close to some transition where there's a chance of charge and spin liberating into these kind of independent degrees of freedom. Okay, so that's kind of introducing the first thing. And the second player that I have is dualities. So we know many of them already from our undergraduate physics, right? The standard ones we learn about is the duality of the Ising model, or the vortex description of the XY model, or the duality between magnetic and electric formulations of electrodynamics. So, and there are, of course, many, many more and much fancier ones. But one of the key properties of these dualities is if you apply it twice, you get back to where you started. And you go from magnetic description, electric description, magnetic description, or low temperature, high temperature, low temperature. That's kind of the very basic things. They look to be somewhat specific to a system, but there's something that one can do, which is, again, apply duality twice, but do something else in between. This something else may look fairly innocent, but actually result in something dramatically different at the end of the day. So an example of that is known as the so-called duality webs in 1 and 2 spatial dimensions, where you have some basic duality. It's called the bosonization duality between fermions and bosons. And if you just apply it twice, you get back to where you started. But if you do something rather innocent looking in between, you change a couple signs, and then you get new dualities, like the particle-vortex duality of bosons or of fermions, kind of derived from this parent duality, which is this fermionization. And there's a one-dimensional version of this. So I'll be talking mainly about this kind of rather well-known and simple duality, which is the particle-vortex duality of bosons. Right, so I have bosons, they have some short-range interactions, and we know that we can equivalently describe this system as vortices coupled to some emergent photon. And so that's the way how it's often formulated. I have some theory of these bosons psi, they couple to some static external electromagnetism A, and I describe it instead as this theory of vortices. They couple to some dynamical gauge field here in such a way that the flux of this dynamical gauge field is just the current of these bosons. And this theory has lots of symbols for describing something very simple. So I'll replace it by some kind of shorthand, which is like so. This has all the information we need. The vortices are coupled to the bosons are coupled to this capital A. The vortices are coupled to small a. And then there's a specific coupling between these two gauge fields, right? So this is kind of a shorthand description for just the standard boson-vortex duality. And this duality certainly has this property that if you apply it twice, you get back to where you started. To apply it twice, I just take this right-hand side and replace this part again by itself. So then I'm getting the consequence, a new object, kind of the vortex within the vortex, coupled to yet another gauge field and these two kind of terms. And the thing to notice here is that A, this is dynamical field here, only appears in this very simple way, only in this gauge coupling and in some linear way, or in other words, just a constraint. So the constraint just tells me that A tilde here is just the minus capital A. So I'm getting a theory which is this vortex in the vortex coupled to my external gauge field, which is of course the same as I had here, just with some minus sign, which is following from my convention. So the boson is just the vortex within the vortex, and this duality, applying it twice, just got me back to where I started from. Okay, so now, so in principle, you can read off, all the properties from this, but there's a useful physical way of thinking about it. Namely, the vortex is essentially defined as an object which has the property that if a boson moves around the vortex, it picks up a phase which is just given by the charge of the boson and the number of the vortices, how many I have in between. Or conversely, if I move the vortex around a certain number of bosons, I'm picking up a phase which is given by the vorticity and the number of bosons which I have encircled. So in particular, if the average boson density, if it's non-zero, is some background field experienced by the vortices, that we already heard this at least once today. And specifically, if I'm at half filling, so I have 1/2 boson per lattice height on average, then I'm these vortices experience pi flux. This is kind of a situation which has been studied like more than 2 decades ago. And the key property is that if I have such vortices in such a background, and I just write down some band structure, I'm getting 2 minima, for the vortex dispersion. So essentially, if I'm looking at taking the low energy limit of these vortices, I'm getting 2 species, one here and one here. Okay, so now knowing that, I can go back to my boson. As I said, the boson is a vortex within the vortex, so it's like a vortex of vortices. But now if I want to put a vortex into a vortex, well, since it's a sum, I better put one vortex into both low energy vortices. That's certainly what I would need to do in order to have a vortex in this capital guy. So I can maybe draw it like this. And now this, the sum of vortices here has turned into a product over here. Or in other words, the boson, which I started with, has now been split into two fractional guys, right? The vortex in vortex 1, the topological defect within this species of vortices is kind of half a boson, and the defect in the other guy is the second half of the boson. And together they form the physical boson which I started with. Right, so okay, so let me just do this exercise of using this kind of schematic formulation to derive what happens. So I start with the basic version of this duality, which I had on the slides a couple of slides ago. Okay, now I have 2 of them. I take the low energy limit. So I'm saying now I have a sum of 2 vortex species. They still couple exactly the same way to the gauge field, and this part is still unchanged. And now doing that, I want to do duality again. But now I have 2 species, so I do duality separately on each of them. So I'll do that. Now I have a slightly more complicated theory. Ji is just the vortex in the vortex I, and now I have a total of 3 gauge fields, A, A1, and A2. But just as before, this A only appears in these terms, so it only enforces the constraint. And specifically, it enforces the constraint that the sum of these A1 and A2 is just the external field A. So plugging this in, I'm getting this theory. I get these 2 species, these kind of particles. They couple to some gauge field A tilde, which is just the difference between A1 and A2. That's still dynamical. The sum has been constrained, so it's gone. And therefore, the capital A has appeared here. That's just, yes. Oh, the first step there was just the fact that my bosons are at half filling means that the vortices experience a background flux of pi per plaquette. And now I'm just asking, what is the band structure with such a background? So I get a band structure with 2 minima. And so I'm just saying, okay, now I'm just gonna expand around these minima. and toss away the short range, the high energy stuff. The left-hand side, yes, this statement here is true when I'm at half filling. That's right. Okay, so that's my theory. So I have two particles. They couple with to some emergent gauge field A, and in the way I've written it down symmetrically, they each couple with half charge to the physical electromagnetic field. But it's a gauge theory, so if we want to understand what it describes, we should ask what are the gauge invariant objects in this thing. So firstly, I can just combine one of these particles, one of those particles, right? And that's just the microscopic boson. And you can just see that this is an object which just couples to the external field with unit charge. That's the thing. But in addition, I have another quantity, which is the flux of the gauge field. That's certainly gauge invariant. And that follows from the duality very simply. It's just the number of vortices of the one species minus the number of vortices of the other species. And there's no reason for these numbers to be truly conserved, right? If you have at least translations, you can easily convince yourself that the symmetry will prohibit you a vortex hopping from here to here, because you'll, if you say a different minimum momentum space, but say moving two vortices or some higher number of them may be allowed by your symmetries, right? I always have translations, so I can never move an individual vortex, but higher numbers may be allowed, but they will be ruled out by other lattice symmetries. For example, if you have square lattice symmetries, I think you can only move kind of 4 of them together. 2 of them are also not allowed. Right? But that depends more on the specific lattice symmetries that you will have. So what it amounts to is that we have we describe the bosons close to the transition as two objects, these two fractionally charged objects coupled to some gauge field which is compact, right? It's compact because the flux is not conserved. So this theory may eventually lead to confinement depending on essentially what type of these objects are allowed. Right? Compact gauge fields tend to confine unless there is enough matter around, or conversely, unless the vortex number is high enough that even a small amount of matter may prevent them from actually confining. Okay, so this is all known stuff so far. So what we already know and what was known some 20 years ago is how we use dualities to go from, or how to split a single boson into kind of two halves. Right? That's essentially old news. And what I want to do today is to use essentially this type of technology to split these spin half particles, or two particles, into these 3 objects. Right? So instead of going from 1 to 2, I want to go from 2 to 3. That's the mission. Any questions before I start doing that? Okay. So my starting point is I take 2 species of bosons, right? So I've kind of 2 conserved, 2 U1 symmetries, 2 conserved charges, the up species and the down species. And as a starting point, they will not talk to each other. They'll just be decoupled. So for each of those, I can apply what we already know separately. So I'm describing all the up bosons in this way by two halves, which you can roughly think about each carrying, half a spin, half a charge, and a quarter spin, for example. These are not super well-defined quantities, but it's useful. Each of them should be separately at 1/2 filling, right? So that otherwise I wouldn't be able to apply this in the first place, right? Say again. Well, okay. So notice I only declare I have kind of U1 symmetries. So that means I only have the conserved SZ. So I know if you want, you can call it 1/2, 1/4, or you can call it 1 and 1/2. It doesn't quite matter. It's whatever. It's 1/2 of the SZ quantum number this guy really had. The quarters will soon disappear. So if they bother you, don't worry about it. Okay, so this is just applying exactly what we know for just boson at half filling. And now I'm again asking about this kind of question, what about these processes where the low energy vortices switch switch there things, because now I want to couple them, right? This is, as long as I get it coupled, that's kind of the end. That's all I can do. But now I want to couple them in such a way that I do preserve these two numbers separately. And so I cannot really write down a term where one boson hops into the other one, but I want to have interactions between them. And the natural way, or one convenient way of thinking about interactions, is within this picture of these vortices. You can certainly think about a process where one vortex hops, changes its flavor, and at the same time, the vortex for the down bosons also changes its flavor. And if under some symmetry, this one gives my term, say, some phase, then for this combined process, I'm getting twice phase. But that's still pretty simple. So it's some process which I may consider. But depending on how these guys transform on my symmetries, there's generically still some non-trivial transformation. So I can imagine, at least if my lattice symmetries are large enough, such a process may still be ruled out from my symmetries, which means that an operator which creates this vortex, and destroys 2 and 2. Right? Notice the orientation here encodes essentially whether it's a vortex or an anti-vortex. So I may have symmetries which prevent this process from appearing on its own in my low energy theory. But there's some other process where I'm just changing the direction here. I'm taking one vortex of the up guys from here to here, and the down guys from here to there. And then as long as these bosons transform equally in a spatial symmetries, then whatever phase I acquire in the symmetry by going from here to here will always be cancelled by the guy here and here. And so unless I have some weird symmetry that acts differently between these two flavors, this type of process will always be symmetric under all my spatial symmetries. So that one is one that I should always take very seriously and put this term into my low energy theory and ask, what does it do? That's what I'm doing now. I'm just saying, okay, this term may or may not be there depending on my symmetry, so I'm going to ignore it for now. But this one is certainly there. And so I declare this is the most important coupling between my two boson flavors. And what does it do? So what does it do? So to check that, I'll take my excitations, like my half-charged quarter-spin objects, and ask if they pick up any phases once they go around this type of object. If they do, they will be confined, and if not, then they're not. That's the rules of the game, right? Because if this entire thing is some huge composite boson, and if it has some relative non-trivial phases with these guys, these will confine if this guy here condenses. And since each vortex here is contained here, all of these guys will become confined. Like this one, because this one here, this part is condensed, this one because of that, and so on. So all these half-charge quarter-spin object, which I wrote down, will be confined if this type of term is relevant, which I would generically expect it to be. That's good. I didn't like them, so now they're gone. Now I should ask, well, what terms are still left? That is now, did I just kill everything and get back something trivial, or do I still have something interesting? So firstly, of course, you can notice that the physical bosons, the physical up boson, down boson, they can never become confined. Right? They're just physically microscopic objects. And that's kind of clear if I'm, just looking at this object here, the physical boson, which is not drawn here, it's just a combination of this one and this one, but it will pick up opposite phases from these two, or the down guy from these two, and therefore the physical boson is impervious to the condensation of this object over here. But it's not the only one. For example, I can take this guy here and that guy there, right? Kind of a half of the up guy and half of the down guy, and just looking at here, okay, this vortex goes here, this one goes the other way. So this object is also unaffected by the condensation of this composite guy here. And likewise, this guy here and this guy here. And now I just count the quantum numbers, right? This one has, okay, I have two halves which add and have plus a quarter minus a quarter, so they cancel. So I get my charge one guy, which I was looking for. I combine these ones over here, right? This is now a particle and a whole. So the charges subtract and the spins add up to 1/2, which is again what I was looking for. And finally, I get the same thing for spin down. So just by not doing particularly much, just by understanding that this is an operator which is always allowed by all my spatial symmetries, and declare, and considering this one to be the most important coupling between my two boson species, I pretty much for free get that all these guys are gone, and these guys here, well, they may or may not be gone. That still depends on what else is going on, but certainly they are not confined directly, but just by this term which couples together my two species. Okay, so these are the three players that I have left, and I can again use this kind of schematic way to derive, at least on this level, that this is indeed what happens. So I have my boson. Right now I have two of them, the sigma. And the first step is exactly the one I had before, right? For each boson, I get two species of vortices, right? Again, and these bosons, they're both at half filling. That's the important bit. And they're coupled. It's just two copies of the same thing. Nothing's fancy here. Then I'm just introducing some new object, v tilde, which is some vortex composite, in this way. And I can just read off how it couples to the gauge field. It will couple in this way. So if I have these two vortices and these two tilde vortices, I still have all the I can still access all possible configurations. So this is kind of one way of parameterizing all my degrees of freedom. But this process 2, which I'd written down, it's just this term over here. It's just the hybridization between v tilde up and v tilde down. So that's an allowed term. And what it's essentially going to do, it's going to say, okay, I only have a single guy left over, which is just v tilde. You can think about just forming, some bonding and anti-bonding states of these vortices. And I'm going to throw away the one which is at high energy and only keeps the one at low energies. So that I have only a single vortex left in this picture. So now I have a single J tilde vortex. So I have now three particles, three objects on the right-hand side. I have, the vortex 2 up, the vortex 2 down, and this J tilde. And now I perform duality on all three of them. So that's a lot of dualities. So I'll just do some counting. So here I have three guys. I have up, down, and vortex. And I have two gauge fields, up and down. And now I do three more dualities. So after that, I have, three matter fields and a total of 5 gauge fields. And 5, yeah. Right, 5, okay, so good. But 5 is good because 5 means 2 of them will be constraints. They eliminate another 2, and the single one is left. Right, that's the counting. So, so, the steps in between are, just 1 or 2 lines which I skipped. So at the end of the day, I'm just getting this. I'm getting 2 objects that I call the spin-ons. They couple to the external field as over here. They couple to the single dynamical gauge field which is left. And the charge-ons, the final guy couples just to this guy also. Right? So this is kind of the low energy field theory describing this thing here when both bosons are at half filling and there is a coupling between these two species, which I've introduced. And again, you can think about what are gauge invariant quantities, and they are pretty obvious. I just stick together the charge and this spin-on, or charge and that spin-on. These are things which I didn't know from the start, but there's again the gauge flux, and the gauge flux is the second process, what I called process A before. It's again some number of these vortices, which is not conserved, and depending on your symmetries, it may either just be not conserved at all, or it may be conserved mod 2 pi or something like that. Okay, so that's it's more or less the main part of the derivation. I want to emphasize that I haven't actually used all that much. Right? My ingredients were, I think, relatively minor. I just said I have bosons. I'm at half filling. We have a transition. And then I couple them. And for the coupling, I just use the operator which looks to be most relevant at the transition. Of course, we don't, relevant is a bit of a dicey point since we don't know that the transition is a true critical point. But that, it's called the most important one. Specifically, this transition, it appears to be some bosonic QD3 with 2 flavors, except that they are monopoles, and depending on this number here, which depend on the symmetries, they are probably confined. So there's some range which may be described by the theory, and that eventually, the ultimate fate may still be confined. But nevertheless, this operator here, which I've used to couple them, which is kind of the the monopole of the one times the monopole of the other one, is presumably a much more relevant one than this guy down over here, right? Here I may have, the force power of a given monopole, whereas here I just have, twice a single monopole together. So this one is presumably important. So one may imagine that if I couple them, this is the most important term. Right? Below this, I get this theory of spin-ons and charge-ons, and then possibly at such a transition, there may still be confinement. So firstly, it may such a transition may still be described very well by these kind of variables. So it's kind of a natural framework to use, but also I can now take this theory and deform it to explore nearby phases. Because, of course, once I have these degrees of freedom, I can imagine just turbulent them a little bit in one direction or the other one. I may get different phases of these degrees of freedom, which may actually result in this thing never occurring. For example, if I get some sort of condensate of either the spin-ons or charge-ons, then the gauge field which I have will acquire Higgs mass, and I will not ever reach confinement. This would not be the statement about the transition, but about some phase which is kind of nearby, in the sense that it's just, I arise from just weakly perturbing essentially this kind of state. Well, it's this. It's the spin-ons and charge-ons, So they're all critical at some transition, right? So all these just have some just, there's some critical boson. They all couple to this emergent gauge field over here, but the gauge field is compact, and well, what kind of monopoles are allowed will depend on what symmetries you're going to impose. So that essentially it depends. But in general, it's just this kind of gauge theory where of these three type of particles, and it's generically going to be compact. Say again? Well, right now there are no fermions in this game. Everything is still a boson. Right. So right now everything is a boson. I meant said bosonic. I think that's what I. Scalar, yeah, that's what I meant. I didn't specify it out. That's right. Of course, you can, you know that if you have this QD3, you can, describe it as some fermionic theory. But at the end of the day, if you do it here, well, you cannot, this one, since it has both these spin-ons and the charge-ons, it will not be. I guess they can in principle all be fermions in some way. So you can have that also. But that's that's the kind of theory. So yeah, so this is mainly maybe the main point of what I want to talk about. Now I'll just talk about what else we can do with that. So if there are any questions so far, this would be a good time to to ask them, I guess. Oh, M. Okay, so M would be the monopole. Right? So this QED is compact. The compactness just being related to vortices changing flavors. So the basic monopole would be the one where one vortex changes flavor from one minimum to the other one. That one is not allowed by translations. But then, the M1 squared is allowed by translations. It may still be allowed by the symmetries. That's the, in the gauge theory, it's a monopole operator, but, more physically, maybe it's really just the vortex changing its type. So both of these copies, initially they're decoupled, should be maybe M up and M down. They have these kind of monopoles. But then the more important coupling than this one is certainly the one where I'm taking the monopole from, say, the up boson and the one from the down boson. And as I emphasize, this thing is always allowed by lattice symmetries. In that sense, it's presumably an important one. Whereas here, you can have a higher power, which again depends on which symmetries you want to specify to. Any more questions? Okay, so what can we do? So the main goal which I started out with was I wanted to get this spin-ons and charge-ons using the duality, and maybe somewhat surprisingly, I didn't actually need to put in very many ingredients. It came out almost for free, which is nice. Then one can get to fermions. That's one thing. Another thing one can do is once I have this duality, I can use essentially known methods to derive it, not on this schematic level, but actually kind of as an exact transformation on so-called coupled wire arrays, and can use the same thing to actually derive, like, semi-microscopic models, which would realize all kind of phases and transition in this vicinity. And finally, there's a Z2 relative of this kind of spin-on charge-on decoupling. So the first one is pretty simple. So I can now start with fermions. Yeah. I think the phases which I had here are all known phases so far. In this phase, you can have all kind of superfluids. You can have symmetry like valence bond states. You can have magnetic states, like all the symmetry broken states. Now I can use this, of course, to get in this scheme to write down models which realize, say, Z2 spin liquids. But again, these are known states in this level. Again, not really. I'm not really getting nuance with these fermions. It's again just saying I can do the same thing, but I can't. Maybe that's what you're driving at. I can't get Fermi surfaces for some reason, and that's something which we can discuss. Something specific about this. Essentially, it's a step of throwing away. I believe it's a step of throwing away the high energy vortices. By reducing it, you're essentially forcing whatever fermions you end up to be essentially an integer filling. So you can't get uncompensated Fermi surfaces, which is unfortunate, but I think it's just built in. Okay, so just the kind of a quick thing what I can do for fermions. Well, if I have some kind of fermions, I can always just recast the fermionic theory as bosons by some form of flux attachment. There are many ways how I can do that, so I don't need to specify it. Right? I can attach to them the total charge, the total spin. I can attach something different. But once I have this, I can use what I already know from this guy over here, right? Replace them by spin-ons, charge-ons. And the key point is that these spin-ons couple to this Trans-Simons guy in exactly the same way the bosons did over here. So I can just take away the Trans-Simons field again and getting some theory of fermionic spin-ons. So I can do that, but again, this doesn't necessarily give me new phases. The simple phases I get in this vicinity will still be essentially superconductors, valence bond states, this kind of thing. Somewhat unfortunately. As that, yeah. So essentially, what I described. If I start with fermions, I am getting this kind of separation into fermions, fermionic spin-ons, and bosonic charge-ons. Of course, you can, depending on how you do the flux attachment in the first place, you can also get a fermion, which is a boson, which is the fermion, and these guys to be the bosons. But at least in this thing, that will always require me breaking time universal symmetry by hand, whereas this one does not. So I prefer this version. One can also just take more bosons and add another fractional filling. Right? I always want to be a total filling integer, so I can form a sensible insulating state. But instead of 2, I can take n bosons at this fractional filling. In that case, I will have many, many more minima in the boson dispersion. So I have lots and lots and lots of the vortex dispersion. I get lots of them, and I can essentially play the same game. I can ask, okay, what combinations of these vortices will confine which excitations? And you get more or less what you'd expect, namely that you can split up n component bosons into into one charge-on and n kind of charge-neutral guys. So you can do that, but but I don't know what you would use it for. It's maybe more of a curiosity, like if you have a good reason for that. And it becomes a little bit messy very quickly because the number of objects you need to juggle around just grows quadratically. So here you already have, you would have like 16 vortices, and you need to ask like which ones are allowed and which ones to throw away. So instead, I just want to, a bit of time left, mention on, that one can take this duality, and in specific models, in these wire arrays, one can actually make it precise. So this is kind of based essentially on some mechanism which we developed in some work a couple of years ago. And, the fact that I can do it is already kind of obvious, because the only ingredient I really used is the basic boson-vortex duality, right? And I did boson-vortex duality, I did a couple of steps, I did another boson-vortex duality. So these are the only ingredients. So if I know how to, how to do the basic one, I can certainly just, just turn the crank and get eventually also this more complicated one on the wire array. So okay, so why wires? Why do they make life good? Why do they allow me to do things? So this is just 1D wires. The point is this: if I have bosons, right, I can describe them by some complex phase. Then within the wires, I have this Latinger liquid, right, which just coupled to the gauge field in the way we think we've already seen today. And I have some interwire terms, right? And so these terms here are quadratic, and these terms here are not. It's sum theory. But there's a very natural gauge I can use in this setup, which is the one where I just set AY to 0. And then I have a theory where the gauge field only lives in the Gaussian piece, not in this nonlinear piece. And the advantage of that is that it allows me to integrate out the gauge field without doing anything, getting anything nonlinear. So I integrate it out, say some gauge field. I'm getting something which is non-local, but still Gaussian. And that's something I'm not so scared about. If it's, as long as it's non-local but Gaussian, I'm still okay with that. It's just that if I have some non-locality in some nonlinear piece, then it gets messier. So that's I think in essence that's why it's useful to use these kind of wires in order to derive things. So then we can formulate some summations. The first step is again I go from these guys, so my up boson to these fractions, and maybe just for illustration, what does this mean? So this object here, and if you do two of these partons, that's an object which would not be gauge invariant in the theory which I derived, right? It's an object that would carry gauge charge too. So it's not an object that should not be local, and it's also not even gauge invariant. So I've chosen a gauge, so there's like at least a unique way of transcribing it, but it's still non-local, and indeed, this is what it looks like, right? It's some infinite string, which has, particle here, hole here, and so on. So it's a bit of a messy object, but you can convince yourself, because there's this string over here, that if I'm not taking this thing here, but now I'm looking at the hopping of this fractional guy, putting a hole here and a particle here, then all the string cancels. And this process I may care about, the hopping of a fractional charged object, that just corresponds microscopically to a hopping of an integer boson between two wires, right? And it's maybe somewhat natural to understand that, okay, if I move an integer by charge 1 from one wire to the next, that's on some level equivalent of moving half a charge by two wires. That's kind of a mapping of these microscopic processes. So in a similar way, all possible processes I can write down where these fractional guys may hop in some way actually correspond to something local in terms of my microscopic degrees of freedom. But so the mapping is non-local, but most of the terms I care about are actually local. So that's nice. And so in my case, the similar thing will apply, that individually the charges and spin-ons will be non-local, but the terms that will hop them will be local. Okay, so now knowing that, I can go back to my Gaussian action. I'm going to get gauge theories of this type, with the gauge field only sitting here and this guy being there. Then I take my gauge theory and I can integrate out the gauge field. So I'm getting something which is non-local, but all the non-locality is in the Gaussian piece. And I'm having some other piece which is unaffected because it doesn't have a gauge field. Now I do my transformation between these degrees of freedom here and those degrees of freedom, like the one which I described, this long string object. And this transformation preserves the locality of this guy over here, but it turns out it precisely cancels the non-locality here and gives me a nicely local action in terms of these microscopic degrees of freedom. Right? So that's the sense in which one can derive the duality. I'm taking a gauge theory, I'm choosing the gauge, integrating out the gauge field. I do this, essentially the operator mapping, this field mapping, and I can show that these partition functions are actually identical. Here, because you're not allowed to expand in gradient, then you can't get many things. For example, you want to have, say, you want to have a phase where bosons may be able to hop or something like that, but also other phases, which this thing is very important. If you just expand that, you're essentially only ever able to get the superfluid, right? Because then you get just grad phi squared. But there may be other phases that you may care about. In the same way as, say, when you take the XY model, like on a lattice, you expand the cosine, you're losing some phases. Right? You're losing essentially the high temperature phase. On these wires, so you notice that in one direction it's continuum, in this direction, but in the other one it's not. Yeah, that's why I put it discrete. Yeah, maybe that was not obvious. Yeah, thanks. Right, so that's how you can do it. You have like, one continuous direction, one the other one, which is maybe unfortunate if you don't like being anisotropic, but this is really the tool which allows you to actually, to write down highly non-trivial theories in a way that you can actually solve them. And in particular, it allows you to, to kind of derive these type of dualities. Yeah, it also allows you to, write down called parent Hamiltonians in this language. There's been like a bit of an industry which has been developing, like these are some early works, and then you can see that starting, maybe 10 years ago, suddenly the number of papers using this really proliferated. And by now you have these kind of, this wire models for about any phase you can imagine. Many gap phases, but then also some for transitions, for gapless states, and and more recently for these dualities. So we have many of them. And now this mapping, this identification of these charges and spin-ons kind of locally allows us to just generate these models very efficiently. Namely, you can write down simple models here, right? It's very, I write down a model where the charge-on is in a quantum Hall state, say, where my one spin-on is in a superfluid, the other spin-on is in a mod state. They're all very simple models. I can write them down, and I just automatically get a local model. That's the important bit, something which is perfectly local, in terms of my microscopic variables, which I can then try to realize, say, on a lattice or something. So that's the thing. But kind of the corollary of this, I can also play this game that I'm fixing this guy over here. And for this charge-on, I'm taking a model with some parameter which drives me across the transition which I know. For example, I can take a model of this one here undergoing a mod transition or a quantum Hall plateau transition or something of this type. But because I've started out with this decoupling, what I'm going to get by this is a model where I can drive this transition, say, without changing the spin gap. That's something that is somewhat non-trivial. If you have some model, which has some phase you may care about, and then you just crank up the interactions in order to get the phase transition, say between an itinerant state and a metallic state, you cannot expect that the gaps will remain nicely closed, and you may just open the spin gap, open the charge gap, and get to something stupid happening in between. So here you can actually write down nicely local models where you can guarantee that you get the kind of phase transitions which one may like. For example, if you think about superconductors, there's a natural way you can think of a superconductor depending on what's going on. It can undergo a transition into quantum spin liquid. Right? That's a phase where your spin gap would remain, but you have this how do you call it? As you go from here to here, the charge undergoes a transition. You get from a superfluid to an insulator. Your spin gap remains finite all the time. But you can, of course, think about the Cooper pair just being some object which leaves behind its charge and then transforms into some resonating valence bond on the superconducting side, which is, of course, just the Anderson picture. And here you can just write down models where this is precisely what happens. And and then similar, you can get other transitions from these models, say from superconductors to symmetry broken states and this kind of thing. So these type of models allow you to really, to write them down, and you can be certain that as you tune some parameter, you get precisely those transitions you care about. You don't get something, something stupid happening in between, which may in principle then allow you to write down simpler ones, which you can say test maybe in numerics. So that's thing. The final thing I want to mention is that there are V2 analogs for all these dualities, right? Essentially, it's almost like a one-to-one mapping between quantities in the boson-vortex duality and quantities in one lower dimension, essentially with Z2 symmetry. Right? For example, is the Kramers-Vanni, like the quantum Ising model, is essentially the same for in many ways as the 2+1 one-dimensional boson-mod transition. And since this 2+1 one-dimensional boson-mod transition is really all I used, right? I used it in many ways, but I just used it as a basic ingredient. I can immediately take what I did in 2+1 dimensions, use this kind of dictionary between U1 and Z2 symmetries, and get some version in one lower dimension. And so yeah, so the mapping is essentially this. I have two species. If I have boson at half filling, this half filling roughly translate into some larger symmetry, the Z2 cross Z2 symmetry. Of the Ising spins, all the U1 gauge fields become Z2 gauge fields. In a specific case, having two bosons amounts to two copies of these one-dimensional Z2 spin models. So it's kind of like a spin ladder model. So in these spin ladder models, you should expect to find analogs of many of these phases and deconfined phase transitions, which you would get in 2+1 dimensions using this spin charge decoupling. So so yeah, that's kind of it. I explained to you, I showed you how can use this dualities to get this separation, the spin charge separation, how to get this spin on and charge on degrees of freedom without too many assumptions. I can take this thing and transcribe it into these wire models to actually derive microscopically firstly the duality and also models that realize varied transitions. And there's some not yet explored, but I think very interesting way of getting interesting analogous phenomena to these in one dimension. Thanks.
Because it is not relativistic, there is no problem to change this to relativistic part.
What they are depends on kind of where I'm in my phase diagram. So so I can be in phases where they're not, where they're generally massive. So I always have a lattice, right? So for example, all my spins, my bosons, they can, how do you call it? They can always form an insulating state. So I'm never truly relativistic. My lattice is always there, and these bosons also know about it. So I don't know if that's what you have in mind.
Okay, so you're saying fractionalization, what you do is you compare the kind of microscopic quantum numbers to the quantum numbers that you're going to excitation, and that's kind of what you've been using. But is there a way to to tell whether, how can you tell if some phase is, when you call a phase fractionalized? I think your way of doing it is to say, well, I compare the quantum numbers of my learning excitation to the microscopic quantum numbers. Is there a way that only refers to kind of symmetries, the emergent symmetries, or not the infrared without?
I mean, this is standard way how you would analyze it. If you're a gapped phase, you would ask for the degeneracies on the torus, this type of things. Or gapless, I don't know. I don't know. I don't know how to make it defined, but I'm sure that there are people here who may have an idea.
Okay, David again.